Right, so section 2.1 was about input and output values, and in section 2.2 we're going to build on that with the ideas of domain and range. So if we let y be equal to f of x, then the domain of f is the set of input values. This is a list or a set of x values that'll give us a meaningful output value. Okay. So for example, the rules of math tell us that we're not allowed to divide by 0. Okay, so if you had a function that you plug a number into and you would end up dividing by 0, then that's not an allowed input value. So it would not be in the domain. All right, and then the range of f is the corresponding set of output values. Okay, so this is a list of y values that we can get out of our function based on the input values that are allowed. All right, so let's look at a practical example of this. So the number of gallons of paint needed to paint a house depends on the size of the house. A gallon of paint typically covers 250 square feet. Thus, the number of gallons of paint N is a function of the area to be painted, which is we're represented with the capital letter A, and that's in feet squared. So we would write N is equal to F of A. This problem has some practical limitations on the range and domain. So what would be reasonable for those? All right, so let's start with the domain. So this would be the area of the room to be painted, or the area of the house to be painted. Would 500 square feet seem reasonable? Sure, that seems okay. How about 2,500 square feet? Yeah, that sounds fine. What if I told you the house had negative 100 square feet? Yeah, that would be a problem, right? So that area of the house needs to be at least bigger than 0. Okay, we know it's not infinite, right? Nobody has a house that has infinite area, but it can be as large or as small as we want, as long as that number is positive. Right, and then the range. So our dependent variable here is the number of gallons of paint. And so what would be reasonable for that? Again, it doesn't make any sense to have a negative number of gallons of paint. So here our range is going to be N is greater than or equal to 0. Probably really strictly greater than 0, not really equal to 0, but we'll leave that as it is. Number 2, Oakland Coliseum is capable of seating 63,026 fans. For each game, the amount of money that the Raiders organization makes is a function of the number of people N in attendance. So if each ticket costs $30, find the domain and range. Okay, so our independent variable here, so our domain is always reflecting that independent variable. That is N, the number of people. And the range is our dependent variable. Okay, and in this case, that's going to be the money or the revenue. All right, so for the domain, how many people are allowed in this stadium? So the smallest we could have would be 0. And the maximum number of people allowed, assuming they're following the law and not letting extra people in, would be 63,026. Okay. So there's our domain, and then our range is how much money they bring in. So if nobody's there, then we aren't going to make anything on the ticket sale. So our lower end of our range is going to be 0. And the upper end of our range, so suppose we filled the entire stadium full of people, that's at 63,026 fans. And we'll multiply that by the $30 cost per ticket. So that upper end here is going to be $1,890,780. All right, so there is our domain and range for the game. And then number 3, so this one has a graph to go kind of along with it. So a sunflower plant is measured every day, lowercase t, and t is greater than or equal to 0. The height of the plant is modeled by a logistics function, which is this guy here. So 250 over 1 plus 24 times 0.9 to the t. And we have a picture of this. So where I would like to start here is actually with the range. So the range would be these height values, our dependent variable here. And it looks like the upper end of this is 250. I feel pretty comfortable eyeballing that and taking a look at that. But this lower end, it looks like it's greater than 0. So let's take a look at maybe see if we can figure out what that would be. So we do know that the smallest little t could be a 0. So if I plug 0 into this function, h of 0, it's going to be 250 over 1 plus 24 times 0.9 to the 0. Well, anything raised to the 0 is equal to 1. So this guy here is equal to 1. Oops, I copied that down wrong. My bad. So what I get is 250 over 25. If we divide that out, that's equal to 10. And 10 seems, looking at this picture, 10 seems like that's plausible based on that picture. So the lower end of the height is 10. So we're looking at between 10 centimeters and 250 centimeters for the range. And then the domain, so again, that's our independent variable that's on this horizontal axis, and that's going to be the time. So we know for sure that little t is greater than or equal to 0, so that gives us the lower part of our domain. And then we need to think about what the upper part of this is. So they didn't put a restriction on it here. If we look at this picture, I mean, it does seem like it kind of just keeps going, but let's think about the practicality of this. Is that sunflower going to live forever? Not unless it's plastic. So what we're going to do is we're going to say, let big T be the day the sunflower dies or wilts. Okay, and so then that makes the upper bound on our domain that big T. All right. Okay, so that's just some of the things to think through in terms of the practical examples. So you want to especially think about, our negative number is going to work in there, our positive number is going to work in there. Is there an issue with including 0? So things of that nature as you look at the practical side of the domain and range.